Hello, the topic of our lecture is the physical basics of electrical machines. My name is Valery Tityuk. I'm professor of Department of Electromechanics in Kryvyi Rih National University. The operation of electric machines is based on the following basic physical phenomena. First, creation of a magnetic field by a current flowing in a conductor. Second, creation of electromotive force in a magnetic field. And last, the force effect of a magnetic field on a current carrying conductor. For the optimal design of electrical machines, the thermal action of the electric current, namely the release of heat during the flow of an electric current, is also extremely important. All these physical phenomena have a fairly deep, proven mathematical description. All processes related to mutual transformations of electric and magnetic fields are described by well-known Maxwell's equations from 1864. The force effect of a magnetic field on a current-carrying conductor is described by Ampere's law. The thermal effect of the current is described by the Joule-Lenz law. The purpose of our lecture is to study the physical fundamentals underlying the operation of electric machines. A comprehensive description of electromagnetic phenomena relies mainly on Maxwell's equations. The description of electromagnetic phenomena is relatively easy when compared with various other fields of physics, sciences, and technologies, since all the field equations can be written as a single group of equations. In terms of higher mathematics, Maxwell equations are a system of partial differential equations describing the state of the electromagnetic field and the processes of its changes in three-dimensional space and in time. In writing Maxwell's equations, the vector operator of multidimensional differentiation nabla and various elements of vector matrix algebra are widely used. The main physical quantities involved in the phenomena are the following five vector quantities and one scalar quantity. On this slide, you see a table with the names, common designations, and units of measurements of the basic physical quantities that we use to describe electromagnetic processes. They are electric field strength, magnetic field strength, electric and magnetic flux density, current density, and last, electric charge density. The direct application of Maxwell equations to describe the operation of electrical machines is impossible due to the complex geometry of the devices and the use of different structural materials. All this make an exact analytical solution of Maxwell equations in relation to electrical machine impossible. The physical law of determining the vector of induction of a magnetic field generated by a direct electric current is called the law of and formulated in a general form by Laplace. Magnetic induction is a vector physical quantity, which is a force characteristic of a magnetic field, namely a characteristic of its action on moving charged particles and bodies with a magnetic moment. A standard notation for magnetic induction is B as vector. Unit of measurement in SI system is Tesla, and the designation in CGS system Gauss. Using the Biot-Savart-Laplace law, we can calculate the induction of the magnetic field created by the current flowing through a thin, straight wire of infinite length. The magnetic induction B of the magnetic field in an arbitrary point A created by the conductor element dl can be calculated using the exact formula. In this formula, we use the magnetic constant. It's denoted by mu0 value. In the International System of Units, SI system, the value of this constant is given on the slide. The direction of the magnetic induction vector B of the magnetic field is determined by a well-known drill rule. This law is determined as follows. If the direction of translation movement of the drill coincides with the direction of the current in the conductor, then the direction of rotation of the drill handle coincides with the direction of the vector of magnetic induction of the field created by this current, as shown on picture on our slide. The individual fields from different current elements dl have the same direction relative to a circle with a radius r lying in a plane orthogonal to the conductor. So we can integrate the models of the magnetic induction vector. The formula for calculating the modulus of the magnetic induction vector is shown on the slide. If the conductor has a limited length, then this will change the integration limits in our formula. Let's express values of r and sine alpha in terms of the integration variable L. We can get these formulas. Substituting these expressions into the equation of a magnetic induction after simple transformations and calculation of the non-self integral, we finally obtain formula for magnetic field induction shown on this slide. To indicate the direction of the current in the conductor perpendicular to the plane of the figure, we will use the following notation based on the analogy of direct current with an arrow. We use cross the tail of arrow when the current is directed from me to the plane of picture. We use point the head of arrow when the current is directed from the picture to me. A picture of the line of force of the magnetic field of an infinitely long, straight, current-carrying conductor is shown on this picture on our slide. The magnetic field lines of an infinite rectilinear conductor with a current form a system of concentric circles enclosing the conductor. The direction of the field lines form a right-handed system with the direction of the current. Let's consider a small example of calculating the magnetic induction of a rectilinear current-carrying conductor. Our example: calculate the magnetic induction of a strength conductor with a current of 5 amperes at a distance of 1 centimeter from the conductor. If we substitute all these values to formula from above, we get next formulas, and our answer is 1 to 1000 Teslas. This is our answer for our example. Consider the magnetic field of a solenoid. A solenoid is a cylindrical coil consisting of a large number of coils of wire forming a helical line. If the coils are wound close together, the solenoid is a system of circular currents having one axis. If we consider the solenoid to be long enough, then the magnetic field inside the solenoid is uniform and directed parallel to the axis. The calculation of the magnetic field on the axis of the solenoid is based on the calculation of the magnetic field of one circular coil with current in it. As the analysis shows, the magnetic field induction on the axis of an infinitely long solenoid is given by the next expression. In this expression, I is a current in solenoid, and N is the number of turns of the solenoid. A solenoid can be considered infinitely long if its length is 20 or more times greater than its radius. The flux of the magnetic induction vector, also known as magnetic flux, depends on the relative position of the magnetic field induction vector B and the surface element ds. The flux of the magnetic induction vector through a small surface with an area of ds is called a scalar physical quantity equal to these equations. This value is calculated as vector production of induction and surface and element of surface. The magnetic flux F through an arbitrary surface S is equal to the surface integral from the vector product of a magnetic induction and the normal vector to the surface in accordance with the formula on this slide. The absence of magnetic charges in nature leads to the fact that the lines of the vector B have neither beginning nor end. Therefore, The flux of the vector B through the closed surface must be zero. This property significantly distinguishes a magnetic field from an electric field. The lines of magnetic induction are closed, so the number of lines entering a certain volume of space is equal to the number of lines leaving this volume. If the input fluxes are taken with one side and the output fluxes with another sign, then the total flux of the magnetic induction vector through the closed surface will be zero. In the SI unit system, the unit of measurement of magnetic flux is the Weber. 1 Weber is equal 1 Tesla product to 1 square meter. Magnetic flux is associated with Faraday's law of electromagnetic induction, which states that a change in the magnetic field in space produced an electromotive force in a closed circuit. This phenomenon is used in induction appliances such as generators, transformers, and induction furnaces. In 1831, the English physicist Michael Faraday discovered the phenomenon of electromagnetic induction in his experiments. Faraday's law of induction, or simply Faraday's law, is a basic law of electromagnetism, predicting how a magnetic field will interact with an electric circuit to produce an electromotive force, EMF, a phenomenon known as electromagnetic induction. That's thanks to this phenomenon, we can convert mechanical energy into electrical energy, and this is wonderful. After all, before the discovery of this phenomenon, people didn't know about other methods of obtaining electric current, except for electromechanical processes. When a conductor is exposed to a magnetic field, an EMF arises in it, which can be quantitatively expressed through the law of electromagnetic induction. The law of electromagnetic induction is as follows. The electromotive force induced in the conductive circuit is equal to the rate of change of the magnetic flux coupled to this circuit. In a coil that has several turns, the total EMF depends on the number of turns, and as shown in this formula on our slide. From this formula follows the well-known rule of Lenz. Electromotive force in a closed circuit has such a direction that the generated electric current, which is induced during the change in the magnetic field passing through the circuit, prevents the change with its own magnetic field. When we operate with an alternating voltage, an alternating current will flow in the circuit, which creates an alternating magnetic field. If the winding consists of n different turns, Then the magnetic flux can be calculated due this formula, where phi c is the peak value of the magnetic flux created by one turn. Then, according to the law of electromagnetic induction, the electromotive force shown in the whole winding will be equal to this formula. The effective value, also known as RMS, root mean square, of this electromotive force, is evaluated due to a given formula. This expression is used in calculation of electric transformer and calculation of alternating current electrical machines. Let's consider a small example of the application of the law of electromagnetic induction. In our example, we have 100 turns in a coil with a cross-sectional area of 1 to 10,000 square meters. The turns of the coil are placed in an alternating magnetic field with an amplitude of 1 Tesla. Frequency is equal 100 Hertz, and a winding coefficient of kW is equal 0.9. Calculate the electromotive force induced in this coil. Solution: when we using the above equations, we obtain next formula and numeric results. Therefore, the peak value of the voltage is 565 volts, and the RMS value of the voltage induced in the coil is 400 volts. The force effect of current. French physicist Henri-Marie Ampère established the existence of a force interaction between two conductors through which electric currents flow. Let there be two long parallel conductors. If currents flowing in opposite directions are passed behind them, the conductors will repel each other. If the currents will flow in one direction, then they will be attracted. Experiments provided by Ampere showed that a current-carrying conductor placed in a magnetic field exerts a force. The force acting on a conductor placed in a magnetic field is called Ampere's force and can be calculated in vector form as vector production of oriented element of wire dl and vector of magnetic induction. This formula is called Ampere's law. To determine the total force acting on the whole conductor, it's necessary to integrate this expression along its length, taking into account the dependence of the magnetic field on the position of the current element of current. Such integration becomes trivial for a rectilinear conductor in a homogeneous magnetic field. The direction of Ampere's force is determined by the left-hand rule. If you place your left hand so that the lines of a magnetic induction enter your palm and the outstretched fingers point in the direction of the current, then the bent thumb will show the direction of the ampere force acting on the conductor. The schema shown on this slide. Consider why the ampere force in this figure is directed downward. Remember that it's accepted that the direction of magnetic field lines of force is from the North Pole to the South Pole. In the United States, a slightly different formulation of this rule is used, known as the FBI rule. Force, induction, magnetic induction, and current. Try to apply this United States version of left-hand rule to our drawing. Let's consider an example of the application of Ampere's law. In our example, we need to calculate the force acting on a conductor 0.1 meters long, through which a current of 10 amperes flows at an angle of 80 degrees with respect to the magnetic field induction vector of 1 Tesla. Solution. Using Ampere's law, we get directly for the magnitude of this force. We know the angle between element of current and magnetic induction, and in the result we obtain Ampere's force equal 0.98 newtons. The thermal action of the current. When an electric current flows from a point with a higher potential to a point with a low potential, part of the energy of the charges is lost. If current flows in the conductor and the conductor is stationary, the work of the electric field forces is spent on heating the conductor. Having collided with the particles of the conductor, the charge carrier transfers to them its energy, which it receives from the field. Therefore, the work of the field on the charges turns, in the end, into the energy of the thermal chaotic movement of the atoms of the conductor. That is, the conductor is heated. The power lost in the conductor due to its heating can be calculated by the well-known Joule's first law, also just Joule's law. This law is also known in countries of former USSR as the Joule-Lenz law and formulated according to this well-known formula. This formula is called the Joule-Lenz law. The law was established by Joule in 1841 and independently by the Russian physicist Lenz in 1842. Acknowledgements. I would like to thank all the colleagues who made this work possible. A special thanks will go out to Professor Georgy Ivanovich Kornilov, my first lecturer in the course of electrical machines, whose lecture notes I still use to this day. Professor Dmitry Rodkin, my first lecturer in the course Electrical Drives. Professors Alexei Chorny and Viktor Busher, my colleagues from whom I'm still learning. Many thanks for all participants of our lecture.